So, for the sake of capturing, I'm repeating all again. This is the paper that we are going to present in the next seminar, in the next conference coming. The name of the paper is "With Whom Do I Interact?" and we are going to detect social interactions in egocentric photo streams. This is generally the outline of the presentation. First of all, I'm going to explain why we are focused on egocentric photo stream and why am I more interested in social interaction. Later on, we're going through the methodology. What is the idea that we had to form a whole of work? What was the type of features that we used to achieve our method, and what was the method in general that we used to achieve our goal. Finally, we will show the experimental results, and in the end, I will draw some conclusion from the work. So let me start with the definition of this social interaction. What does it mean? Social development in 1978. Social interaction is a process by which people act and react to those around them. And it has multiple applications. It can be useful in design and implementation of the social robotics. It could be useful in politics and marketing because sentiment analysis is very important. This can have applications in the health and so on. This list can grow. As I explained it before in my previous presentation, there are multiple factors that can define the social interaction. And it could be, the most important ones are actually the pose of the people, their orientation, the direction that they look towards it, the expression of their face, their dynamics, and so on. But it's mostly about the people. Then we get to why we are interested in egocentric social interaction, and this is my favorite slide. I always put it in whatever presentation I have. Why egocentric data analysis? Well, I always refer to these two papers. First is saying that taking photos can impair your ability to remember. And then there are another study which is saying that Sensicam has already made its impact on the memory enhancement. So we already know that why we are interested in egocentric images. But why social interaction in egocentric photos? Because it can be helpful in detection of unhealthy, detection of unhealthy social behaviors can be useful generally for the people, and especially for those who suffer from the memory impairments. And for this study, we need long-term study of these people, and to this end, those cameras who have low temporal resolution are most suited. These photos that you can see here are the photos that actually are captured by the narrative camera. Who is there and with sort of interacting, and how is the type of the interaction? Is it funny? Is it formal? There are different questions. But specifically in this work, our goal is that having a sequence of images, we want to answer that who is interacting with the camera wearer. There are several challenges coming with the problem all in all, and with this type of images in specific, that can be divided in two categories. First of all, first of them comes from the low frame rate of the camera, which results in the sparseness of the observation. You do not have much information. Well, we do not have much information, and on the other hand, we are capturing a lot of images, so we have a lot of data to process. And the second category is the unpredictable camera motion, which results in the changes of the field of view, the hue changes in the appearances, and the background clutter, all of these things. And having all these challenges, we still are looking for a solution to solve our problem. Social scientists have previously tried to answer this question, that how can we, just by looking at the image, answer the question that if there is a social interaction or not. So this is a random image, random photo from the Google. It's a coffee break of a conference. But just looking at this image and trying to find groups of interacting people, maybe the first one could be this one, and the rest can be found easily. But if you look closely to this image, all these groups of interacting people, they all try to form a circle. This phenomenon has been found and described by Kendon in late 70s under the name of a theory which is called effect formation, that the people tend to make when they interact. And it basically is defined by the position and the orientation of the people. It is comprised of three spaces. There is a P space where the people are standing, and there is an O space where the people who are engaged in a social interaction are looking inwards to it, and there is an R space where the people who do not belong to this interaction are standing in this space. An effect formation has different types. Here you can see, but we will not go through it. So we kind of employed this idea of effect formation to answer the question that I posed before, and this is the general scheme of the method that we follow to achieve our goal. And I'm going through the diagram step by step to explain the methodology. So having a camera, it would give us a set of images, and then let's assume that we have our sequences where there are people in it. We simply call it a sequence. A primary step towards any human behavior analysis is first, in the computer vision, is first to localize them in the images and in the videos. And once you do it over the time, they simply call it tracking. So the first step of this work also is to track the people in the images. But due to all those challenges that I already mentioned, all of the state-of-the-art trackers failed. So here what we needed was a tracker that was capable to deal with all those challenges. And to this end, we used a previously introduced model by us, which was able to overcome all these problems, and we used it to track all the people in the sequences. The next step in order to apply, in order to prepare all the features to be usable, to be fitted into effect formation, what we needed to know, as we saw before, effect formation needed the location, the position of the people, and the orientation of the people. But the position of the people that it needs is in the 3D space, is from the bird view model. So here we had a 2D image, and what we needed to have was to know the distance of the people from the camera wearer. So to this end, what we did was to what we did was to train a regression model, polynomial regression model, to learn this conversion. And basically, what it was learning was the relation between the distance and the height of the face of the people. So as the people were further, their faces were smaller. On the other hand, we do not use the information of the camera very explicitly, but just knowing that where it stands is implicit information that we need to know. So we imagine that the camera wearer is set on the where it is, and in the middle of the scene, and from the 0 distance from the camera, because the camera is worn on his chest. The next information that we need was the orientation of the faces of the people, also to be used into F information. And to this end, what we did for all the tracked faces, we just increased the bounding box that we found, and we applied an orientation estimation method for this, and we decreased the threshold so it could find it could find the orientation with better accuracy. And in the case that it couldn't find it's sometimes in some frame it couldn't find the orientation, we just make an interpolation between the neighboring frames, and we found the right direction. Also for the camera, where in this case also it's we do not know where he's looking, as I said, because the camera is born on the chest. So we just consider for him like 180 degree of freedom, but we put the probability on this that he's looking at the other people. So doing all these things, now for each frame, we have the position of the people in the 3D space and also their orientation. And we do this for every frame. And doing this for every frame, finally for the sequence, we will have a two-dimensional signal for each person, which is indicating its orientation and their distances with regard to the camera wearer. So the next thing is to use all this information and employ a sequence level classifier to classify these signals into socially interacting or not interacting. As a classifier, we used LSTM. We relied on its ability to learn the temporal evolution of the signals. In this work, we used the revised version of the LSTM, which used the full backpropagation through time for optimization, which is based on a matrix-based match learning, and the revised activation function, which finally results to a more robust and much accurate results. In our experiments, we use the homemade dataset. This dataset is made by 80 users overall of 100 days, which results to 3,000 images, where among them, like about 100 sequences containing the trackable people, average length of 25 frames. The sequence contains of 75% of people interacting and 25% of people non-interacting. And then later we divided this data set into 70% training, 15% validation, and 50% test set. Later on for the validation, to train our model, we just augmented the training and validation data set, and we just tested on the test data set finally. Another part of experiments is to choose the right parameters. Well, choosing parameters, optimizing parameters is always a very difficult task and machine learning. In this work, we use the random search because, well, it's easy to implement and parallelize, and it also very uniformly cover all the search space. The different parameters that we tried to adjust was were the number of memory cell block, learning rate, momentum, and batch size. We also have used two different optimization techniques: limited memory BFGS and the mini batch gradient descent. By using those parameters, here you can see that the model finally converged using both of the optimization techniques. And let's go to the results. We compared our results with there are there are a few techniques which are focused on social interaction analysis on the images and videos, and for the problem of social interaction analysis on photo streams, almost there's no work. So the only work that we could compare our work with was our previously introduced work, which was, well, we called it HBFF, which is almost, well, I'm not going to go into details, but it's a frame-based work, and in each frame it decides if there is a social interaction or not, and finally it decides if there is social interaction or not for whole the sequence. But basically this method is a frame-based method, and the other method that we presented in this work is a sequence-based method. And here you can see the results between different methods is not so bold. They almost perform the same, but the final result using the sequence-based method and using the stochastic gradient descent as an optimization function, has led to best results. Here are some of our qualitative results. The first two rows are considered as socially interacting, which can be seen that they are socially interacting, and the second two rows are not socially interacting. As the conclusion remarks, we could say that, to the best of our knowledge, this is the first time that the effect formation is being analyzed in the sequence level using LSTM in a way that we extract the social signals in the frame level, and then we analyze it over all the sequence. And there are several problems has remained open. Well, to name a few, is to employ contextual information such as motion, body postures, so on, to see their effect and the results, and also as much further works are like finding social roles and defining type of the interactions. And that's all. Thank you.
Okay, so now we do the same exercise. Advices to Maya to improve